I go there Tuesdays and Thursdays because I have 2 back-to-back classes in the main hall, and I don't get out till 2.
Oh.
So
I forgot that they serve food when the caf serves like late lunch or something.
Yeah. So I'll go there and just late lunch.
Hi, friends. Hello. Got all your awesome lunch conversation to start off our. So let's settle in. I brought a little, just slightly different mechanism for us to come into presence here. So let's just, if you so choose to join me, just sit up a little straighter, be a little more aware of your body, and let's just dive into the sound. And when it's done and gone, we will start. I think it's gone. I have old ears. True to the test you can do on social media where they play the pitch and they can guess how old you are by when you stop hearing it. Have you ever seen these? Mm-hmm. Yeah. I've got the ears of a 51-year-old man. Spring chicken. All right, so exam 1 coming back to you. If you haven't checked out World Class, there's details on how to do corrections. So when you get this back, I grade with the intention that corrections are an available remedy for whatever your grade is. So you can get back 50% of the points you lost on something if you lost more than 1 point. If you lost 1 point, just that's it. I probably gave you the answer. It was probably just some like plus or minus error. Bigger point deductions for bigger conceptual misses, and well, I'll just shut up and get these back to you so you can see. You could get 110 out of 100 because you did the bonus. That's the maximum possible. And there was a number of over 100% papers. I gave partial credit on the bonus. I don't usually do that, but I did this time. Basically, you probably got +2 or +10 on the bonus, depending on how that all went. So, first thing to do, make sure that what I have taken off is accurately reflected in your grade. If it isn't and I owe you points, please let me know. Let's just do this. So take a moment, go through there. So I'll just put a few things up here. We have a new web work that'll open after class today. Web work. Yeah, I think it'll open after class, or at least toward the end of class, because we got a lot to do. And then exam corrections are due what did I say? Does anybody remember what, I think I said maybe the start of class on Wednesday. Let's start there. Let's try that and see how that goes. I may or may not be on campus on Thursday and Friday. I'm not quite sure of that yet, so I would like to get these before I left. So let's just say Wednesday. One thing I would like you to pay really careful mind to is the format in which I request the corrections. So you're gonna have, your top page is going to be your original exam. So you're gonna have your exam, and then underneath that, you're going to have your corrections on separate paper. Your corrections, I've got all the steps that you need to do. Honestly, also, if you got over 100%, please don't do corrections. My God, just stop. Just stop. So your corrections at the back of, I ask you, what did you do wrong? What needs to happen? So there's a couple of parts to that. Please make these nice, because it's a chance to recoup. The easier this is for me, the better it'll be for you. Absolutely. Make my life easy. Make it easy reading is mostly what I'm concerned about. So is there any questions at all about any of that stuff? Yes?
If you have like questions about like some of the comments, just
Yeah.
shoot you an email.
Yeah, absolutely. Yeah, absolutely. Yeah, so yeah, I would want you to have time to talk about that. So now I'm wondering about that Wednesday due date. Yes, let's do that. Let me think about that due date, because I want to get them before break.
Yeah.
You know, like at the latest. But yes, please ask questions if there are things to chat about, and we'll talk about it. Yeah, absolutely. Any other questions? No? Cool. Most excellent. And I will release full solutions once corrections are submitted. I just don't want to hand them out until those are in. All right, we are gonna do linear algebra boot camp this week. Who in here has had linear algebra? Pretty good. Who has not? That'll be easier to see. That's cool. That's all right. So we're gonna focus on the very basics that you need to get through this, and we'll work together. And Brandon, if like anything, let's talk. Let's engage as we go through this. We are gonna focus on 2x2 things. So 2-dimensional things is it. Everything we're about to do for the rest of the semester could be extended to as many dimensions as you'd like, but 2 really gets you a good understanding of everything we need. So here's our motivation. What is about to happen? We are going to study systems of differential equations. And this is completely different, really, than anything we've done so far. What do I mean by systems of differential equations? Well, I've got 2 differential equations that may or may not be linked together. So we have something like this, and it generally will be in x's and y's. I've got a dx dt, and it depends on, and we're going to look at a very specific form to start with. It depends on some constant times x plus a constant times y, and all this is referring to the plane. So we're going to look at the plane, and I've got a point xy, and by computing this quantity here, so a, b, and also c and d are constants. By computing this quantity here, I can find the velocity in the horizontal direction. You can think of this as horizontal velocity, the horizontal component of the velocity vector. And then I also have another one, dy dt equals cx plus dy. This has a very specific form. It is called a linear 2x2 system. we're going to do nonlinear things because it gets weird and awesome and strange. Nonlinearity is the world. Linearity is what we pretend the world is to understand the bigger nuttiness that is happening before us. So, we will not get to this for a while. I want to talk about, I'm going to try to show us just the route from this to linear algebra. So first off, this thing here can be written as follows. I've got a vector xy, so this is a vector, and in fact this one's going to be a velocity vector. And all it is just these two things locked together so that they are an inseparable quantity. I'm going to put a little dot over the top for DDT-ness. I got a derivative of some vector. The thing to remember here is that x is a function of time and so is y. Both these are going to change. They're both functions of time. And that's just my velocity vector, and my velocity vector can be computed by knowing my position vector, xy, so literally this thing right here. If you take a point in the plane and you draw from the origin to that point an arrow, you get a vector. So this is the vector xy. I use this notation. This is also completely legit notation. Some people put a comma in there to separate. Like this, you don't need a comma, but here you might. Those are the two main forms of vectors that we're going to use here notationally. This is called a column vector. This is called a row vector. But they mean the same thing. It just depends on how things are rolling and what format you want. We're probably going to stick with these most of the time. So up here, I'm going to have a matrix. And a matrix is going to encode these coefficients. So I've got A, B, C, and D in there. That's a constant matrix. And it is going to completely determine everything about what is happening here. And what is happening here is a flow in the plane. So you just got done dealing with flows on the line. You had something like this. And that was a flow on the line. And we saw that could be pretty interesting, right? We got sinks and sources and things that aren't either in there. This is going to be a flow in the whole plane, so a table filled with currents. And we're going to put leaves onto the table and watch where things flow. So it's a little like the direction fields that we've seen, but much more complicated. Much more complicated than any direction field we've seen so far. And in some ways easier to understand, even though it's more rich in structure. So this is a constant matrix. Let me refresh your memory on how to do matrix multiplication really quick. So this is a matrix times a vector. But a vector is also a matrix. It's just a special kind of matrix. So vector is to matrix as a square is to rectangles. This is just a more general form of that thing. Every square is a rectangle, every vector is a matrix. A vector is a matrix that only either has one column or one row. So one of its dimensions is completely flat, just like these guys right here. Okay, so where are we going? So matrix multiplication, how do you multiply two matrices together? How to multiply two matrices. So the thing to do is you've got a matrix and you've got another matrix, and I'm just going to go through here by an example. Let's stick with 2 by 2s. So I've got two matrices I want to multiply. This is times in here, so this is matrix multiplication. Can anybody describe this? How does this work? What would you say if you were teaching someone how to multiply two matrices together? You're tutoring for linear algebra. You've had linear algebra, most everybody in here. Boy.
Isn't it like two matrix vector multiplication?
Yeah, can you say a little more? You're right.
I mean, first we take the first vector and multiply it by the matrix, then we take the second one.
Yeah, and so then there's four actual vectors we could think, right? There's that, and that. So, yeah. The basic idea is this. You're going to use these rows here, and you're going to use the columns in the second one. And the basic idea is, if I say dot product, does that make sense, Brandon? Does dot product make sense? Does that phrase make sense to everyone? Because that's what it comes down to. You're going to take the dot product between a row and a column, and that's going to tell you what is in the output row and column. So for this one, I'm going to take 1, -2, and I'm going to dot that with this first column. So this is 2, 5. So this is row 1, column 1. And that means it's going to produce row 1, column 1 here. When I do this dot product, it's 1 times 2 plus -2 times 5. Notice how it's component-wise multiplication and then add up the results. So let me write that out as a little reminder and a nice way to say it. The dot product equals the sum of component-wise multiplication. Component-wise multiplication. So this turns out to be 1 times 2 minus 10, so -8 goes here. Could you just real quick make sure everybody's doing it? Finish the rest of this for me, please, and then we'll come together. And I see folks do it in their head. That's totally cool. Sanity check real quick. This is row 1, column 2. So I take row 1 and I dot it with column 2. And that gets me that output. And that's going to turn into a 1. 1 times 1 plus -2 times 0. And then we'll keep going. Now I'm going to use row 2 for row 2 of the output. So we get 15. And then 0. Is that looking okay? Yeah, Brandon. Awesome. Any questions or concerns with that at all? Kind of a more basic thing that we need. But it shows us how to multiply this. So if I'm giving you just this, can you see that that is actually this? And the way to see that is you're going to take this vector dotted with this. See, I only have one column here, so I'll only have one column of output. Let's do it together just to be sure. So take the first row times the only column we have, and it's a times x plus b times y. And then second row, only column of output, cx plus dy. And so this is a very compact way to encode this system over here. Let me know. Good? Yeah. All right, where are we going with this next? Wow, we made it through that page. Let me give a slightly even more compact notation. So we represent matrices, and a matrix is just a grid of numbers. It's just literally a freaking grid of numbers. It doesn't have to be any more than that. It can be a lot more than that, but it doesn't have to be. So we represent matrices. Sorry, put that plural with capital letters. This is classic math culture and science culture, I think. So I could take that system over there and say that A is this matrix here. Just call it capital A. That's going to be convenient at times to just say matrix A is this grid of 4 numbers. I can also encode the vector, and so I want to show you some notation today that's going to be persistent throughout probably the rest of the semester. So usually a vector, we like to put little hats on them just to make them look different. So if you have a printing press, you can make bold things and stuff like that. So, but we're going to put this hat indicates vector. So I know it's a one-dimensional thing, either this way or this way. And this is our coordinates. So this is just xy. This is my position vector. So I can rewrite that system in a very beautiful way, and that looks like this, as x dot equals ax. So this encodes everything about that system. As long as I know what A is, I might not know what A is and just want to be talking about things that look like this. The cool part about this is if I understand things about how this works, this A could be any size. I could have something like this, like a 4-dimensional, I'm not going to draw a 4-dimensional matrix, but this X could be a 4-dimensional beast. And then things get weird. We can't draw it. If I had a 3D one, if we had a 3D one, we could imagine a flow in this room. Air currents, let's say I'm a physicist and I'm trying to model the flow of currents. I'm trying to model the dynamics of a fluid. I would have 3 coordinates here, 3 coordinates, and this would be a 3x3 matrix, and it would model the vectors of change in the room. Stop. Does that sound okay? Yeah, okay, cool. Good. Cool, so we are gonna back away from Diffie-Q for a day or so, probably 2 days. We're gonna pull back and we're gonna study not just some basics about what we're gonna do with these things, but I also wanna give you some intuition as to how to geometrically think about this. And it's something that our book doesn't even go into it. So I've got a little bit that syncs up with our book. I don't know what chapter this is. Anybody have their book? No, you got your laptops. Go ahead, Boyne does. Boyne, do something helpful with that laptop for me, sir. I don't know if you have easy access to the book, but I would recommend doing some reading. Let me clean up. Boyne is getting that for us. This is one of my favorite things. How many folks have heard about eigenvectors and eigenvalues? Cool. That's going to be the heart of everything we do. And I will take everybody along. We're all going to be there. We're all going to understand eigenvectors and eigenvalues. And I'm going to wager you understand them better than you did before. That's my hope. That's my great hope. Boyne, you got that book for me, friend? Let's see, so it's, can you move up over here? Yeah, so 3-1, thank you. So I would suggest reading section 3.1 in the book. If you need additional materials, I hope you know how to find them. You go to YouTube and you type linear algebra basics or eigenvector help. And lots of help will arise somehow. And your flavor, your favorite flavor of help will arise. I'm often baffled that folks don't do that more often. So let's pull back from DiffEq and just talk about systems of equations. Because understanding this is essential to getting to where we want to get. So a system of equations, and here I mean linear equations. Sorry, I should have put that in there. Linear just means our variables aren't anything but just themselves to the first power. There's no squares or weird e's or anything like that going around. So I've got a system. Now let's call that alpha, and then let's see, x plus dy equals some beta. And here, a, b, c, d, alpha, and beta are real numbers. And I'm going to use a little math notation. This symbol means element of. In other words, in the set of real numbers. And so this fancy R, and I've probably used it before, but why not say it again? This is real numbers. The goal is to find the x and y that make this true if that is possible. So problem. Find x and y that satisfy the equations if possible. Don't forget to add that, because it's not always something we can do. And it's not always something there's a unique solution to. Sometimes we'll have infinitely many things that are the solution. And let's understand why. Let's instantly, with 3 pictures, understand what I'm talking about. What is the graph of this in the plane? What is the graph of that? You plot out all those. What do you think? A line. It's a line. Yeah, right? If I gave you this and said, hey, can you graph this? I hope you might put it into, y equals mx plus b form, or get 2 points on the line and connect them with a straight edge, or just an imaginary straight edge. So each one of these represents a line. So these represent lines in the plane. Boy, that's getting weird. I'm just taking myself up here with that sentence. The plane is denoted as R2, a real and another real, put together orthogonally, like this. So this is just the symbol for the plane, R2. And notice how I'm saying that. I'm saying R2. So, what do these things look like? Well, one could be a line like this. That might be this first one. Let's say that's ax plus by equals alpha. And it could be that the other one looks like this. The solution to that system is the place that satisfies both of them. So that point of intersection of those 2 lines is the solution. So we have a unique solution at the intersection. But it doesn't have to fall like this. These lines can go all sorts of ways. So we have 2 other possibilities. It's also possible that one of the lines looks like that, but the other one is parallel to it. So here we have 2 parallel lines, and they don't intersect. Now, in our geometry class that meets after this, parallel lines might intersect. We haven't quite got there yet. But in normal geometry, Euclidean geometry that you're used to. Parallel lines don't intersect in the plane. So it's possible that there's no solutions. There's no common place shared by them. And then there's also one last possibility, and they're actually they're the same line. Each equation represents the same line. Not only do they have the same slope, but they have the same y-intercept. So this is infinitely many solutions. Any point on this line is on both lines, so you're good to go. We're going to spend some time today talking about how to know what is what. In particular, the key thing we want to worry about is, do I have a unique solution or not? And that's going to turn out to be really easy to discern. Do I have this, or do I have one of these two? Once you get down to these two, you got to get a little more nitty-gritty with it all. Is there any questions over anything that has happened at this point? Good.
I'm just stuck on like how parallel lines can intersect.
So, you shouldn't have said that. So imagine I'm on the globe. Here's the Earth, right?
Yeah.
Here's you see. So here's me, and here's you. And we both head due north. Follow our compass, heading true north. We meet at the top. Even though we're both headed in exactly the same bearing. So on sphere, a line is a line of longitude. And they all intersect. So in here, all lines intersect on the sphere.
And they're all parallel.
They're all parallel, yeah.
Fun.
Well, yeah, I guess these are still, yeah, I don't want to get it. Let's not get into it. Okay.
No.
Yeah. But does that make sense? Yeah, cool. I didn't mean to hang your head up on that wild fact. So, all right, what do we got here? So let's take this and rewrite it as a system using matrix notation. So in matrix notation, let's call this star. Star looks like A, B, C, D times X, Y vector equals this output vector, alpha, beta. Stop for a second, make sure that you see that that is true. Do the multiplication in your head to just get your brain, slowly warming back up on this stuff. See if you see that those are the same. And I'm gonna wait until everybody tells me they see that. So nod, yeah, just nod or like just thumbs up, just move, thank you, beautiful. Just acknowledgement, yeah, thank you, move, yeah, that's good, okay, good. You got head bobby, good, heads bobby, Tyson's your head bobby. Okay, cool, awesome, thank you, yay. So, step one toward understanding this is to put it into this form. Now this thing is a matrix, I'm gonna call it A. And it turns out that we can solve this system if something is true about A. Now think about just real numbers. Let's just come back to this. So like just a real equation. If I said something X, AX equals B. When can you solve that? This isn't weird. There's nothing weird going on there. They're just real numbers. When can I solve that for X? What happened? Sorry, go ahead. Or did you say something? Who said so? Oh, yeah, Carmen. Yeah.
0, the trivial solution.
Zero is definitely about, so maybe what I'm looking for is a little weird, but you're thinking in the right place. If A is not 0, I can solve this. Yeah, so if I were to tell someone, how do you solve this? Well, what would be the solution? It would be that. And I can only do that if A is non-zero. In other words, if the inverse of A exists. So if A is invertible, it's not 0, then I just multiply both sides by A to the -1, and I get my solution. Does that make sense? Good, okay. Same thing happens here. I can solve this if I can find the inverse of this. So the solution would be this, and I'm going to write it, and then I'm going to talk about what it means. A, B, C, D with an inverse alpha, beta. So let's put a little note here. If we can find this, the inverse of our matrix, our coefficient matrix, we can solve this. It's going to turn out that this is just another matrix. And once I can compute the inverse matrix, I just multiply it by this right side and I get my solution. So let me stop and let you write that. Let me start cleaning up. Any issues or questions? Everybody feeling good? Okay. So, when and how to find this thing, which we could denote as A inverse, if A is this thing right here. So now, if I call this A like this, AX equals Y, it makes sense that it looks just like this thing that I had up before, right? Just like that. And these have little hats on them because they're big things. So can someone help me out here? When does this exist? When can I find the inverse? It's kind of like the not zero thing, but yeah. What?
The determinant doesn't equal 0?
Determinant is not 0. So Lou just said some stuff. If you hadn't had linear algebra or it's a little dusty, that might have sounded weird. So when does A inverse exist? This first thing, Lou just gave us, and this is the one we really want. This is the key one. The determinant of A is non-zero. Well, the determinant of a matrix is we note if we signify that, at least in this class we will, det of A, put parentheses if you want. Determinant of A is equal to what? Can somebody, hold on, let me get this up. Let me write out what I want here. Anybody know that formula offhand? Somebody not Lou?
A times I.
Say that again.
A times I.
A times I?
Yeah.
What's I? Oh,
The-
what is I?
I forgot what it's called.
Identity image?
Yeah, identity image.
Oh,
The one with the diagonal 0.
gotcha, you got your identity matrix. Yeah, no, this is actually a single number. This will be a number that comes out. Does anybody remember how to find the determinant? Oh yeah, I know. I'm sorry. Not trying to diminish you there, just trying to get some other folks involved here. Anybody remember? Okay, Lou, help me out.
It's AD minus CD.
Thank you. And I'm just gonna go alphabetical, just gonna go like that. So you literally just take, now look at how the rhythm is. This is how you'll never forget it again. It's the product here, AD, the product here, BC, negate this and add that. So it's the positive downward right product minus the downward left product. and we get our matrix determinant. So let's actually practice a little bit. Can you find a couple, just find a couple here? So let's see, so we got 1, 1, 1, 1. Let's do that one. Can you find that one for me, please? And could you please also find this one here for me?
Is the second one and the first one, like the first row, is that a negative?
That's
Oh, okay.
good question, Tracy. Yeah. Pretty ambiguous looking. Yes. Thank you, friend. And you're just getting out a single number. Beauty. Almost, yeah, except sign on that. There you go. Lou, Ms. Lou, can you help me with this one? What'd you get on this one?
-1 and 1 is -1.
Negative 1, yeah.
-1 is -2.
And then get a 1 here,
Yeah.
and then put a negative on it, so -2. Does this sound good to everybody? Yeah. Cool. Okay. Awesome. And can you help me out, my friend?
Yeah, -1 times -2, so then 2.
So +2, beautiful.
And then 1 times 2, and then add the -1 there,
Cool.
and then 0.
0. Solid. Thank you. I can find this inverse. I cannot find this one. The determinant is the equivalent of being 0 or not 0 for matrices. Does anybody remember the term for a matrix that is invertible? What is that called? Sing a song, non-singular. Okay, so here, when does A inverse exist? When the determinant is non-zero. We call such matrices non-singular. A couple of ways to remember that. You can just think of a singularity as dividing by 0. You know, like a black hole, some kind of crazy shit. Like that's the division by 0 in our universe is a black hole. But you could also think it has a partner. It's got an inverse. So it's not single, it's got a partner. Right over here, me, my inverse, right over here. We mesh together perfectly. So when does A inverse exist? That is enough for us. There's actually a list of like 99 conditions that make this true. And if you took linear algebra, you probably had to remember some god-awful list of equivalences, like the rows are linearly independent, the columns are linearly independent. Do you remember any of this? Is any of this stuff causing like trauma to arise? Yeah, right? The row space is something, the column space, oh my God, there's so many, there's this huge freaking list. This is all I care that you know. I can find an inverse when that beast is not 0. So what is the formula for the inverse when it exists? So if A is this critter, A inverse is, now here's how I kind of remember this. I'm going to put the 1 over the determinant out in front. And my goal is this. I want A times A inverse, and this is what Voyn was thinking about, to equal the identity matrix. This is the equivalent of 1 in matrix land. This is the identity matrix. Just like 1, but a little bigger, little richer, more stuff going on. So this is the thing we want to be true. So you can kind of work this out in your head. You know that you want this row times this column divided by this thing to give you 1. So in other words, I want AD, and then when I do this times this, I want BC, but I want it negative, so I'm gonna put minus C here. So now check it out. When I take AB and I dot it with this, I get AD minus, whoa, easy, buddy. I mean B down here, minus BC. So I'm taking this and I'm dotting it with this, AB. What the fuck? I'm screwing up, sorry. Apologies. Yes. So this, AB dotted with D negative C, is this quantity right here. And so I would get a 1 up there. And then similarly, or you just write this down and remember it, this is gonna be minus B and this is gonna be A here. So don't worry about all that nonsense I was just saying, know this formula. This is your friend right here. That to find the inverse of a matrix when this is non-zero, and you can see now why it has to be non-zero, you use this formula. So could you do me a favor and please crank out the inverse of this thing here, this first one. This one doesn't have an inverse, but let's find together the inverse of this matrix. And it's another matrix. What is that matrix? You've already got your determinant. Remember, this is just the determinant. So that's cool. It's just 1 over the determinant.
Dr. T.
Yeah, Lou.
So, so A in the formula is positive, but A in the matrix is a negative 1. So do I just make the negative 1 a positive, or I keep it the same?
Yeah, so okay, it's a good question. So let's identify what is going on. So this, I want to mesh this up with the A, B, C, D. So here, this is A equals negative 1, B equals 1, C equals 1, and D equals 1. And that sounds cool, right?
Yeah.
Okay, so when you come over here and you do this over here, Lou, you're just going to take the opposite sign. So the A and the D actually stay the same sign, but they flip positions. So D goes up here, A goes here, and then B and C get negated. So I just make if this was negative 1, I'd make it plus 1. But it's positive 1, so it becomes negative 1, and then opposite of C is negative 1. Does that make sense? Cool. Corbin, yeah.
Is your determinant supposed to be 1 over negative 2 or 1 over 2?
Thank you. Good call. Yes, many thanks. Yeah, just copying that over. So now you've got this number out in front. This just distributes to all the numbers inside. So you want to take this number out in front and multiply everything in the matrix by that 1 over. So my actual inverse is negative 1/2, positive 1/2, positive 1/2, and positive 1/2. And that's A inverse. And we're going to just, for sanity check and see this in action, we're going to double check to make sure that we actually found it. So, is that looking okay formula-wise? Everybody get the same thing? Okay, cool. All right, we're good. Okay. So let's check. I'm going to take A times A inverse. So that's going to be, this matrix is A, so I've got minus 1, 1, 1, 1, times my buddy that I just made over there, negative 1/2, 1/2, 1/2, 1/2. So let's check. This row dotted with this column. You get positive 1/2 plus 1/2, 1. Make sure, maybe just take a minute and check this out. so you can practice your matrix multiplication skills and see, God, I hope I got it right. I think I did. I think I'm good. Gives me a second to figure out what comes next too. Cool. Oh yeah, boy, we're cruising. It gets heavy in just a second here. Okay. So, get negative a half plus positive a half, negative a half plus positive a half, 1/2 plus 1/2 when I take that and that. We're good. That's the identity. And that's how I know I got the right answer. And I can do this in either order. This is also the same as A inverse A. If I had done it that way, completely okay. It's one of the rare times that I can commute. So just make a note, in general though, AB is not equal to BA with matrices. But it is in this case. We're good to go here. If they commute, it's very special. And yeah, this is called matrix. I'll just write it out in a fancy way. Matrix multiplication is not commutative. Cool. Okay, I'm gonna move up in abstraction. Is there anything you'd like to talk about more here? This is pretty, there's not much beyond what you've seen here. If this all makes sense, you're good to go. You just gotta practice it, right? And then it becomes a little better feeling. Okay, so we're gonna use that determinant in a different way. And I kind of alluded to it already. Oh shit, did I start recording?
Yes.
Oh thank God, okay. I don't want to have to make a little mini lecture of all this. Oh my God, yay. Okay. So where are we going here? All right, let's spend a little digression on vectors in the plane. So vectors in R2. We're going to talk about notation and some just basic ideas behind these. So every point, x1, x2, see I'm getting a little more abstract just with notation, just using those indices instead of xy. Every point xy in R2 determines a vector. The vector is literally plot the point out, make an arrow from the origin to that point. What is the difference between a vector and a point? It looks like the same thing, but can somebody tell us, like, what's different? Magnitude, yeah, good, cool, magnitude. Got the length of this arrow and what else?
Direction.
And direction. So a point is just a location. If I draw this arrow, suddenly I've got a magnitude of that arrow and a direction that arrow is pointing in. A point doesn't give you that stuff. So determines a vector which has magnitude and direction. Cool. We will, I'm just looking at my notation here that I want to talk about. We can use some notation here. Let's just use some notation. I'm going to use just V for my vector. So suppose that V1 is a vector, and I'm going to use that column style. So I've got x1, y1. Now I should have called that y1, but whatever. This is all good. It's good to practice with lots of different things. And V2 is x2, y2. So if we were to draw these are two different arrows in the plane. This first one has a tip that ends at x1, y1. So if that's x1, that's y1. This is v1. And if this is x2 and this is y2, there's the tip. I've got v2 looking like this. Its tip is on that point, this tip is on that point. And I'm just gonna call each arrow v1 and v2. Okay, so two vectors in the plane are linearly independent. So this will be spelled better, especially if it's the first time you're seeing this. At least write legibly. Independent if, let's call them, let's say v1, v2. We should put those in there. Can somebody help me out here, linear algebra friends? What does that mean? And I'll take anything. There's about a billion ways to say this too. Cormac, you seem kind of up on your linear. I don't mean to put you on spot either.
Only the trivial solution works for them.
So yes, in what way?
If they were like set up as a system of equations, only 0, 0 would work if they were set equal to 0.
Yeah, that's nice. So Cormac is thinking of if I have a constant times v1 plus a constant times v2, and that's equal to 0, this is the 0 vector right here. That means that the only way that can happen is if both those things are dead. So that's, yeah, absolutely. Can somebody say, yeah, Lou?
Could I say that both vectors have no solution?
How do you mean? So be more precise.
Like if you set them up in a matrix and then you solved, if you like reduced the matrix, then like in the end it would have no solution.
We're close there. So there's definitely some of the right ideas in there. I would have to put too much on the board, but let me come back to what you said. But there's truth in what you said there. There's also a not truth, but toward the end.
You could say like if like the first vector does not equal the second vector scaled, like if they're not like scales of each other.
Yeah. And this is the route we're gonna go. This one's a little easier to see. They are linearly independent if they don't describe the same direction. If it's not a repeat of information we already have. They're literally independent lines. They're not the same line. So this one's intense. This is like if we were taking linear algebra, we would definitely focus on this one. But for us, and this is all you need, for us, if they don't point in the same direction or opposite directions. And that's exactly what Lou was just saying. I'm going to write that out. Lou was just saying that they're not just multiples of each other, i.e. not scaled versions of each other. So let's look at a couple examples. And that's all you got to know for us and everything we do the rest of the semester. So examples. Let's say I have V1 is 1, -2. V2 is equal to -3, 6. V3 is 0, -2. So let's draw these out. So V1 is 1 over 2 down, pop an arrowhead. There we go, so there's V1. V2 is 3 left and 6 up. So it's got a little arrowhead right there. And you're gonna wanna make it look like it's aligned with that one, because it is. It's literally just a scaled version of V2. Let's draw them first and then we'll write that out. But V3 got its own thing going on. V3 is this dude right here. That is a whole new direction. So what multiple could I say? V2 is equal to what multiple K of V1? -3, exactly. If I take V1 and I multiply it by -3, which means -3 times this, and -3 times this, I get this. And so this says that V2 is a scaled version of V1. And let's tie it back to what Cormac said. Notice that that means that 3V1 plus V2 is actually just zeros everywhere, the zero vector. So I found a non-trivial combination of these things that add up to 0, and they are linearly dependent. So these two, V1 and V2, are linearly dependent. You know one, you got the other. There's no new information provided. However, V3 and V1 and V3 and V2, absolutely. So V3 is linearly independent with either, shit, I'll just say V1 or V2. Lou.
So that means that linearly independent vectors can share a solution.
When you say share, did you say share a solution? Yes. I think I know. When you say this, what does this mean in your head?
That means that like this vector is going that way.
That's it. Yeah, they just point in freaking opposite direction, completely different directions.
And like there's like a shared point in the middle, right?
Yes,
Plug
0.
into X and
100%. Yeah, we always think of vectors as originating here, so they'll all have that in common. But they'll all point from here. So like if I just draw this in instantly, that's now independent of anything else here. If I take this and I go straight up, that's now dependent on that one. As long as they don't describe the same line through the origin. That's another way to say it. So let me actually put that up because that's pretty good. If they don't point in the same or opposite directions, if they are not on the same line through the origin. Does that help, Lou? Does that sound good?
mm-hmm.
That's pretty good too, I like that. Thanks for helping us come to that. It's a good characterization. Any other questions, friends? Okay. Cool. So let's see. All right, so how do we determine this? Let's say you can't draw a picture. Here's how you can determine with a simple tool that we already learned whether or not they are dependent. So two vectors, V1 equals x1, y1, and V2 equals x2, y2 are linearly independent. They don't point in the same direction. They don't land on the same line through the origin. Linearly independent. If I create a matrix out of them, either I use them as the rows or the columns. So notice here, I'm just plunking these in. So this is V1's here, V2 is here. Make them the columns of a matrix. If that is not 0, then you're good to go. So, And this can be rows or columns, or, so I'll just put it up here, or determinant of x1, y1, x2, y2, doesn't matter how you do it, you're safe. So that's a way we can discern if they are. Once we know that they are linearly independent, why do we even care? Because they allow us to describe any other point in the plane. So y is linear independence important. So if I have two vectors and I know they're linearly independent, so let's say, suppose that v1 and v2 are linearly independent, which I'm just going to abbreviate really quickly like that. And let me draw a picture of them. So here's, let's say there's v1, and then here's v2 over here. Say they look like that. Once I know that they're separate, I can describe any other point in the plane using these two. What I've got are new coordinates from navigating my way around in the plane. Physicists do this all the time. They take a local frame of reference, right? Is this true? I don't know. Help me out, physicists. You got local frames of reference? Yeah. And that's just local coordinates that help you navigate about where you are. So instead of using, you actually do this all the time. We've got two vectors that we really think about without knowing. So we've got E1 and E2, and these are just the ones that point on the x-axis and the y-axis. These are called the elementary vectors. These are elementary vectors. That's what the E is for. And I can take any point in the plane and write it as a linear combination of these two. These point in the most different directions you can have. 90 degrees, orthogonality. That's as far apart as you can get. So these two here, if I have a vector, let's say v1, v2, I could just write it as a v of these. So think about where v1, v2 is. Let's say it's out here. Let's say, so this is v1, v2. I just move v of these to the right. So I move v of these, v1 of these. Take this 1, multiply it by v1, you get that coordinate. So that's just v1 there. And I multiply this one by v2, and it takes me up to here. So plus v2 times 0, 1. So in other words, v1, e1 plus v2, e2. And I've written any point, any vector in the plane is a linear combination. That's the phrase here. Linear combination of those two. Same thing happens here. You tell me any point you want. So I say like, oh, what about that one right there? How do I describe that using these? And all you do is you kind of pull out a local frame of reference. These are the only two directions you're allowed to move in. So you say, okay, how many of these do I have to move out? So you move out to whatever that multiple is, and now that part's described, and then you move up here to the appropriate multiple. And this guy right here is just going to be some scaling of this plus some scaling of this, and that'll get you that vector. So if they are linearly independent, we can write any other vector in R2 as a linear combination. I said that and I didn't write it. Now I'm writing it. Linear combination of V1 and V2. What time are we at? Oh shit. We're going to be talking more on Wednesday for sure. So i.e. a scalar times V1 plus another scalar times V2. These are the coordinates of the point that we're trying to describe in our new frame of reference. So these are the coordinates. If you took linear algebra, MT 415, I would imagine one of the most painful and horrible parts of that whole experience was change of coordinates. It's pretty brutal. It's really hard to wrap your mind around. Good news, you're not doing it in here. But this is what change of coordinates is all about. Moving from describing things in the way we're used to, how much left, how much this way, how much this way, into new weird shit. Now I have to somehow get to Cecil from using that direction only and that direction only. So if I want to get to Cecil, you can't even see that, but I'm going to do it anyway. I don't care. I'm going to do it anyway. So here's my old vectors. How do I get to, here's the origin. How do I get to Cecil? 1, 2, 3, 4. Awesome. I think I've done this before to you. You've been in a coordinate situation before. So 4 of those. 1, 2, 3, 4. 4 of those. 4 of standard coordinates gets me to Cecil. But what if I've got some weird ass stuff like this? So these are kind of pointing in a angled way. I've kind of got these at like 45 degrees. So let's see, what do I get for Cecil? It's 1, 2, 3 and a half. Now I can only see that. Was that? Now I got to move in this direction. Oh, I got to back up because I can only go that way or that way. So I got to back up. So let's see, what do I do here? So 1. That's it. Just one of those, and then this other direction. 1, 2, 3, 4. Cecil very kindly trying to ignore me as I do that. Fair enough. So the coordinates in this new system are 1, 4, because that's how many of these I got to go and how many of these I got to go. Let's end. That's it. So the web work has opened. You can totally start on it. Don't mess with the eigenvalue stuff until we talk, unless you're really, jazzed. Then do it, please. Thank you, friends.